Okay, good morning. Let's get started. So today's plan is to finish chapter 7 and move on to chapter 8. So last lecture we come up to these slides for the parallel binary adder and subtractor. So we learned how to do the addition and subtraction using only one adder. So this device that we have in hardware. So how do we do that? We actually utilize the two's complement form to replace the negative number and then add that to the so add that value so to replace the subtraction. So in the hardware, as we can see here, we have an adder, 4-bit adder. So A4 down to A1, that's one value, and another 4-bit value is B4 down to B1. So this carry in bit C sub 0 is ADD over bar /sub. So that actually is used as an indicator for either adder or subtractor. So and that signal is connected to the input of these 4 XOR gates. So we also talked about why we need to do that. So XOR gate actually generate the output. So XOR, one input for these XOR gates are B. So if it's an adder, so the output of this XOR will be the true form of B. If it's a subtractor, because these XOR gates, one input will become 1. So if it's a subtractor, this carry in bit is 1. So sub is 1. So B will be XOR 1, and it will generate the complement of B. So that will be our ones complement, and add this carry bit in, which is also 1, that will be our two's complement. So this is how to generate the two's complement using an adder. Now that's a quick review. Let's have a look at how do we write down the VHDL code for this adder and subtractor. So again, we have the entity defined as add sub 4G. So that's a 4-bit add sum. So this sub add sub is input 1 bit. A and B, they are bit factor 4 down to 1. C4 is the out bit, so carry out bit. Sum is also 4-bit bit vector. The architecture, within the architecture, before the begin of the architecture, we have defined a component. So we learned about component declaration and component instantiation last lecture. So let's have a quick review. The component defined here means that this component has already been defined in another VHDL file as an entity. Now we are taking it over and use it within this VHDL file. That's why it's a component here. So we don't have to define it again. So this full adder, we had a look at last lecture. So you can find the full adder VHDL file in the previous slides. And in addition to this component, we've defined a signal, 2 signals, which are internal signals. So signal C, bit factor 4 down to 0. That is a 5-bit signal, and it's a carry bit. So we have to have 5-bit carry bit. Why is that? because we have a carry in C0 and the carry out will be C4. So in total, we actually have 5-bit carry. So this is a bit vector 4 down to 0. So signal B com, so that's the complement of B. So that is a bit vector 4 down to 1, also 4-bit. Okay, this is the main component, main architecture of the main body of the architecture. So first of all, we have sub assigned to C0. Remember, C is the internal signal. Sub is the external port. So we assign sub to C0. Adders. So here we actually are using the adder components. So before we do that, we have adders. So this is just the indicator. This is the block name for I in 1 to 4 generate. Dash dash, that's comments that doesn't synthesize. We need to indicate what we are doing here. So invert B for subtract function, B I XOR 1. So that is the XOR gate. And we have to do 4 of them in parallel. So that's why we have these 4 generate. So B underscore com I get assigned with BI XOR sub. BI is another input port. So we are actually XOR these 2 input ports and generate the internal signal for that. So this is repeated for 4 times and run in parallel. So we have to have the concept of running this in parallel. And as I said, if I ask you to write down these 4 generate in the parallel manner without this 4 generate statement, you should know what to do. So just replace this I here with number 1 to 4. So that means everything here, these 4 statements are running in parallel instead of in sequence, one after another. So that means we are not running B1, B subcom 1 get assigned with B1 XOR sub, and then followed by another statement for B underscore com 2 get assigned with B2X or sub. Although we write down it in such manner, one after another, but in the hardware, they run in parallel at the same time. That's how we do hardware acceleration. That's why we use FPGA to run this code, and it can run, potentially it can run faster than general PC, because general PC doesn't have a parallel running function. So that is the key point we have to emphasize again and again in this class. So to get this into our mind, to know we can run everything in parallel. And then this statement is the instantiation of the component, the full adder component. So it gets instantiated for 4 times. So let's have a look at this full underscore add. This is the name of the component. Port, we have port map. So this port map corresponds to the port defined in the component. So we have port map I, that means that actually corresponds to the first port defined in the component. So where is that? So let's have a look at here. So this is the declaration of the component. And the first port is A, second port is B, third port is C in, and the fourth port is the output C out. Let's have a look at the instantiation. So this is the first port. So that means AI get connected to A here. So A is a part name of the component. AI is a corresponding part of within this entity. This means we are connecting AI to a part of the component. So when you are writing VHDL, the key point here is to have a schematic in your mind, or just simply draw the schematic, because the VHDL here is to connect the external part to the internal signal, or to the internal signal that connects to a component input port. So these four components port are connected to the signals within this entity we are defining. So that just simply means the wire connections. So point-to-point connection of a simple wire. So this is how we do the port mapping within VHDL code. So its corresponding action is when we are drawing a block diagram, we have to connect the external port to internal components port or internal signal. So this adder definition for the full adder port mapping is basically doing that for us. So after we do that, we have this C4, which is a carry out bit for the false full adder. We are actually connect that bit to the external C4, which is the entity port. Okay, so that is the main body of the VHDL code. I will have a quick check of your question here. Okay, no particular question for this. So let's move on. Overflow, we talked about the overflow definition. Let's have a look at how to write VHDL code for the overflow. For the overflow, if the sign bit of both operands are the same, and the sign bit of the sum is different from the operand sign bit, an overflow has occurred. It basically means if you add two positive number together, it doesn't generate a negative number. If you add two negative number together, it doesn't generate a positive number. So if the sign bit change, that means you have an overflow there. So overflow is not possible if the sign bit of the operand are different from each other. So that basically means if you add a positive number with a negative number, it won't generate overflow. So it won't go beyond the range that we can represent within this defined number of bits. So the corresponding so the overflow example here is so we have two overflow examples. One is the first one is two negative values. So we have 80H, that's a hexadecimal. Convert that to binary, we have 10000000. So this is the decimal number minus 128. So we add two of them together, it generates an overflow. So this overflow bit is the most significant bit, is 0 now. That is our sign bit. So we can see we have two negative value add together, generate a positive value. that is an overflow. That is an overflow. So some bit overflow, we have the overflow bit carried over to the next bit. So bit 9, we don't have 9 bit. So that is a positive overflow. And so two negative value added together create a positive number. That is impossible. That is an overflow. The second example is to add two positive number together. So we know that two positive number together numbers add together should be positive number. Instead, here we have the positive number turned into negative number. So that bit actually is a sign bit overflow. So it's a wrong indication that is an impossible case. We know that is an overflow. So how do we detect this overflow in HDL code? We have to figure out the logic behind that. So the sign bit SA is a sign bit of the A input. SB is the sign bit of B input. S-sum is the sign bit of the sum. So the logic behind it is the overflow bit equals SA and SB and S-sum not. So that indicates when SA and SB, they are both positive, but the sum bit, sign bit is negative. So that means there is an overflow. Or the other case, the other possibility is SA not and SB not and S sum. So that indicate both input are negative value, so SA, the sign bit for A is negative. So it's and SB is so I have to repeat this now. So SA and SB, this is 1 and 1 and 0 actually. So basically this is a negative case. This is a negative case. So because we use 1 to indicate that is a negative value. So that is SA and SB, so 1 and 1. Two negative value doesn't generate a positive value. So the second case here, SA not, SB not, indicate this is a 0, 0, generate a positive sum bit, sign bit. So that is a positive, generate a negative sum bit. So be careful about the indication here. So it is clearer if we just look at the truth table of this Boolean expression. So in this truth table, we have 3 input that gives us 8 different combinations. Only 2 of these output are 1. So that is when sub A and sub B, they are both 0, indicate they are both a positive number. S sum is 1, indicate the sum is going to be negative value. So in this case, the overflow bit is 1. So that is 2 positive value give us 1 negative value. That is one case for the overflow. The other case of the overflow is 2 negative values, both sub A and sub B, both SA and SB, they are 1. So that's 2 negative values. It will create a positive sum value that is indicated by the S sum bit. So in this case, we know there is an overflow. Only these 2 cases give us an overflow bit. So this is our truth table. And you can write down the Boolean expression based on this truth table. So that is the logic behind it. And this is the circuit of it. We are using sum of product circuit to indicate this sum bit. So this should be straightforward for us to draw the block diagram. And so because we don't have the HDL code for it, should be very simple for us to write it down. So V equals to SA and SB and S sum naught, or SA naught and SB naught and S sum. So this is just a simple Boolean expression. You can write down it with a AND gate and OR gate expression. BCB adder, BCB code is a binary coded decimal or 8421 digital BCB 8421 code. That's another name for the BCB code. So how do we configure the hardware adder to form a BCB adder? So it's very simple. Just put this 2 input into the input of the 4-bit adder. The only thing we have to be careful about is the carry bit. It's a carry bit. So the sum is the input to the 4-bit input of a binary to BCB code converter. So that is the BCB adder circuit. So we have the 2 4-bit input, A and B. So they are both BCD digit. So it means we only use 0 up to 9. So we ignore 10 to 15. So we are only use the 10 combinations there for the BCB code. Add them together, we have this 4 sum. And this 4 sum will be connected to the binary to BCB code converter. So we learned how to write the VHDL for this part, and we know how to generate the VHDL code for this binary to BCB code converter. So for the carry bit, we have the C4 prime carry bit out of the 4-bit adder output connected to the input of the binary to BCB code converter C0 carry in bit. So this is the total sum bit will be the BCB digit output, and the C4 is going to be the carry output for the total BCB adder. So this is the BCD adder circuit. Okay, so might be useful for your lab work if you are having a multiple digit display for the 7-segment BCD coder. Okay, that's the end of our chapter 7. So